pleasure to speak here. I grew up in the Swiss Alps, although in the better ones, in the Italian-speaking part, but it's still a pleasure to be here and see that beautiful mathematics is being made. So I'm going to talk about state spaces in 3D n equals to 4 theories, and what I'd like to do is to bring maybe a little bit more down to earth what Justin was talking about this morning on that, and maybe related to some things that Martin was talking about yesterday. So here I put a summary of the stuff that I'm gonna use about 3D n equals to 4 that is being discussed. It's been discussed by Justin, so I'm gonna focus on 3D n equals to 4 gauge theories defined by gauge group G. I'm going to take it to be a product of unitary groups for the sake of this talk. And then some quaternionic representation that's of the form T star of M, where M is some unitary representation. Then, as Justin said, there are two topological twists that one can define. Physically, one might think that if we work in the cohomology of one supercharge, and then translations are exact. There are two equivalence classes of these supercharges. We may pick one, QA and QB. And I am also going to work on transversely holomorphic foliations, as Justin was doing this morning. It means that we have a U1H times U1C R symmetry. This will induce Z times Z grading on the space of operators, states. Justin has spent a few words on this. I'm not going to be overly careful about it. I'm going to just use it. We then have symmetries. Some symmetries are the three-Hamiltonian isometries on T star of M that commute with G. So you can write it explicitly as the normalizer of USP M G mod G. And these are going to have a maximal torus, and I'm going to denote the respectively algebras G, H, EH. There is also another symmetry that Justin has not talked about, which comes from pi1 of G, and the consanguine dual of pi1 of G. Physically, this is what measures topological charges of monopole operators. I think Justin's going to talk about it, but for me, I'm just going to be interested in an element of the algebra, which is the real Fi parameter, which Justin has introduced this morning. And I'm also going to turn on some real masses. And there are spaces that are fairly important in the 4 theories. One has already showed up. It's the Higgs branch. Can be defined as a hyperkähler quotient. Here I'm going to just I'm going to use an algebraic symplectic description in terms of a complex moment map that comes from the G action of T star of M. It was what was mentioned this morning. And I'm going to take a quotient with a stability condition determined by the phi parameter. The symmetry of C acts as isometries of the Coulomb branch, but I'm not going to talk about that. And then there is 3D mirror symmetry that exchanges many things of these two. So many things that are in this list for two given theories. In particular, the A and B twists are exchanged, Higgs and Coulomb branches are exchanged, and the respective symmetries are exchanged under 3D mirror symmetry. So this was a very quick recap of what Justin has discussed. And now I'm going to consider, so this is the setup. I'm going to consider the 3D TQFTs A and B on a configuration that is like a real line, R, times smooth, compact, and connected Riemann surface. Of genus G. And the idea is that, at least the physical motivation behind the story is that this kind of setup preserves what is called an equals to 4 supersymmetric quantum mechanics, A and B. That is a theory on the line preserving some supercharges that is valued in field configurations on sigma. So this is just for the physical motivation. What I'm going to be interested in is, in particular, two observables. So one is the vector space of ground states on sigma. I'm going to call this H, and you can think about this as what the TQFT assigns to the Riemann surface. And from this you can recover what is called the Witten index, which is a trace over this vector space, where the trace is graded by parameters that are the fermion number, that is a node grading, and grading parameters for the symmetries FH and FC. So this is schematically. So the Witten index has a long history in the realm of supersymmetric localization techniques. In particular, it has been computed using what is called Coulomb branch localization techniques. That was building on work of also Chris and Boulevard. But then one of the motivation behind this research that I'm going to present was to kind of understand other supersymmetric localization techniques that are more related to vortex equations. And so basically these path integral computations have been like the driving inspiration to kind of construct all of the things that I'm going to talk about. So I should mention that the work I'm presenting is based on a series of works that I've done with Matt Bullimore and Hyun Kim, and a paper of mine, a preprint of mine that was on the archive earlier this year. So my outline will be to provide an explicit computation for HAB in terms of vortex equations data. Let's put it like this. And two, I would like to point out how the physics suggests that there are, even in simple examples, there are some geometric actions of local operators in these quantum mechanics on these spaces. So the first part is work based with Matt Bullimore and Hyun Kim. The second part is based on this preprint that was put online earlier by myself. So I'm gonna make some simplifying assumptions throughout. So. In particular, I'm going to assume that for generic zeta, where zeta was my Fi parameter, the X branch MH that I defined there in terms of a stability condition determined by zeta is a smooth algebraic symplectic variety. And for generic M, the fixed locus of the induced action on this variety has only isolated fixed points. Okay. So, in general, these assumptions. In general, these assumptions they divide TH and TC into chambers. And for the sake of this talk, I'm going to just always pick one, although it's interesting to study what happens when you go from one chamber to the other. I'm going to be a little bit more explicit with what I mean by that. So, a classical example is G is UK. M is the n copies of the fundamental representations, and my assumption holds for n greater or equal than k, where the X branch is the cotangent bundle to a Grassmannian. And TC is essentially R, and it cannot be 0. Whereas for TH, I have an isometry acting on here that is basically PSU n. I have R to the n minus 1 parameters, so R to the n parameters, and I can, so the chambers are given by an ordering of that, so I'm going to have n factorial chambers. And I'm just going to pick one. So, this is just to give an example. Now, let us focus on the A-twist. So Justin has already made me a favor by introducing the vortex equations this morning. And so on the setup, on my setup, which is R times sigma, what I meant earlier by field configurations on sigma, where the target space of my quantum mechanics can be localized to a set of solutions to what are the vortex equations on sigma. E squared is the coupling that wasn't appearing before. Physicists tend to make it explicit, just treat it as a parameter. So we have the vortex equations, and here I am separating the real part from the complex part, as Justin mentioned this morning. So I'm going to have a complex equation that sets the complex map to 0. And then I have the Dirac equation on these configurations and time-independent solutions thereof. They become holomorphic conditions on some sections where that I am for a bundle that I'm going to write down right now, but it already appeared just in stock this morning. So A is a connection on a principal G bundle P, and X is a section of the associated representation M, but twisted by the square root of a canonical bundle, which is equivalent to the choice of a spin structure. And similarly for Y, I'm going to take a section of the dual. So this is just writing in component what Justin put sigma this morning. So I'm going to start with some naive computation. So the expectation is roughly that so the Hilbert space of states in the A-twist corresponds to the rank homology of the moduli space of solutions. What do I mean by that? I mean that this is certainly what happens when the modular space is smooth. And in general, when it's singular or when it's a little more complicated, it's something that is going to resemble the rank homology. And so let us immediately start with an example. So I take G is U1.
It's like half the moduli space, right? You can have like the perverse sheaf or half the moduli space.
Yeah, that's right. Yeah. I'm going to be more explicit later on.
Yeah, I was just trying to, just because I said it this morning, I just wanted people to remember.
Yes. Okay, so basically G is U1 and M is C in the fundamental representation. Here we enter the realm of what Martin was discussing a little yesterday, because I'm going to take zeta to be positive. The vortex equation becomes this, and I'm going to have X to be a holomorphic section and Y to be 0. So this is a classical standard abelian vortex equation. And sorry. And then you can write down the modular space of solutions to this equation. So it's going to decompose into disconnected components given by the degree of the gauge bundle. And so in this case, it's labeled by Z. And And D, in this case, is there is only one modulus, which is the number of vortices I have on the curve. Sorry, the location of the centers of the vortices. And so this is going to be a symmetric product whose of sigma, parameterizing the vortices, whose power depends on the degree of the line bundle. So this parameterizes divisors P on sigma for for this parameter, when this parameter is greater than d plus g minus 1.
Why isn't it just the degree?
Sorry?
Why isn't it just sim d of sigma?
It's because I'm twisting by the power of the canonical bundle. So X is a section of the line bundle D plus half a power. And so I'm getting this shift here. It's an example of, well, physics likes to do that and to kind of symmetrize things in this way. It's some sort of symmetrization in some way. And so, in particular, there is basically the parameter zeta bounds how many vortices there can be, and when the moduli space is non-empty and when it's empty. And so there are sort of word crossing phenomena when you pass z through one of the values of the degree. And I would just like to mention that this phenomena can be captured by integral computations in a very interesting way, but I'm not going to talk about this today. In any case, I'm going to, for the sake of this talk, always take z fixed, but send zeta tilde to infinity. So that I am allowed an infinite amount of vortices on my curve. So basically then, but
So can you? What is this space you're describing? Is this MH for this theory?
sorry,
What is this M that you're describing?
what is?
Yeah, what are you describing? Is this M? Is it MH? Is it MC?
Right. It's the modular space of solutions to these equations.
Ah, I see. But it's neither MH nor MC.
No. Yeah. I'm just calling the modular space of solutions to the equations by M, and it decomposes in terms of the degree of the bundle.
Okay.
And each component is essentially a symmetric product of a curve, parameterizing the centers of the vortices.
What is in the denominator? I cannot read.
It's E squared times 2 pi.
So if you send e to infinity, for example, then the vortices become point-like. Right?
Yeah, that's right.
And but here it doesn't matter which.
Yeah, I'm gonna take volume to infinity, for example, of the curve in my limit. But I'm gonna keep zeta fixed.
Also, can I go back to Johnson's question? Is it really the half of them, or
Well, it depends on what you mean by half. I mean, there are fermionic contributions that kind of build the tangent space, and basically the result you end up getting is the Durham cohomology of sim, the bosonic part, as Justin was saying this morning. So, but I'm going to be a little more precise later. But so in this case, it's going to be the space of states is going to be the cohomology, the Durham cohomology of MD for all D, and you can write this down in a very nice way if you keep track or tweak a little bit your gradings.
I asked one other thing about zeta. Is there, when zeta goes to infinity, there's a nice algebraic formulation of this moduli space where you just forget the real equation.
Yeah, I'm going to talk about that.
Is there such a formulation in intermediate chambers as well, where you somehow use some...
I think in intermediate chambers, so if you don't send this parameter to infinity, I think at least, yeah, I think it's a bit trickier to find such a formulation. This is like the statement that for each Kobayashi correspondences, when you take these parameters to be very large, the stability conditions simplify. For people who know what that means. But so you can, if you keep into account the gratings that I wrote here under TH, TC, no, sorry, under U1H and U1C, you can write this in terms of symmetric powers of a vector space. Hat means that I'm going to multiply by a square root of the determinant of this vector space for grading purposes.
So this is your space of states? Or?
Yes. Yes. Where V is as a graded vector space, I can write it down like this. I have to explain a little bit what's going on here. So essentially, it's a graded vector space with two bosonic components and two fermionic components. These originate from the fact that the symmetric product of a curve has one generator in degree 2, and one in 0, 1, and one in 1, 0 that comes from the 0, 1 and 1, 0 forms on the curve. And if you tweak a little bit your grading so that you shift it each time you go up in degree, which you must do from a physics perspective for reasons that I'm not going to enter to. But if you tweak your grading in this way, what you get is essentially, you can essentially write the homology in terms of this Fock space generated by two bosons and two fermions. Okay, so this is the first computation of a Hilbert space of states. Now more generally, more generally, there can be an intricate. So if the parameter zeta tilde that I defined before hits the co-character lattice of G, there can be solutions to the equations of localizing to where the gauge symmetry is unbroken. And solutions to another set of complementary equations open up, which means that I have in physics terms Coulomb branch directions that have nothing to do with vortices. It's very nice to study an interplay with these things, but for the sake of this talk, I just stick to vortices. And so I'm also going to take this parameter to infinity in a chamber in order to essentially allow an infinite number of vortices. And this, as Tudor was hinting at, how much longer do I have? 20 minutes?
Just, yeah, 20 more minutes. So.
Yeah. Should be fine. So more generally, what you can do is to solve the solutions. So we want to model the moduli space of solutions in a finite algebraic way, which is kind of hinted at by the physics, which means that we have our moduli space of solution that still it's divided into components, topological components dictated by the degree of the gauge bundle. And then we want to write algebraically each component in terms of a moduli space of twisted quasi-maps. And so what that means is basically a set, so a moduli space of pairs where each E is a GC bundle, and X, Y are holomorphic sections of an associated bundle, which is exactly the same associations as before. I'm going to call them EX times EY. And subject to the complex moment map equations. And a stability condition, which in the limit I was taking can be, roughly speaking, be interpreted as the fact that these sections hit the X branch at all but a finite number of points. The intuition is that in this limit, basically, the contributions of the curvature become very small. And if you remove star of f from my equations, you get back the X branch equation. So algebraically, you can model the modular space of solutions in terms of these quasi-map spaces.
E is what GC bundle is?
Yes, it's complex. I'm complexifying the bundle. Yes.
And what is E sub X, E sub Y?
E sub X, E sub Y are the associated bundles to GC that were earlier the associated bundle to G, but I'm complexifying everything, and I'm modding out by GC, by gauge transformations. But essentially, it's the moduli space of stable quasi-maps of twisted stable quasi-maps to the X branch, where the word twisted comes from the fact that I am twisting the sections X and Y by powers of K. Now, why is this useful, and why is this what we are supposed to do? So this is because in the physics you can inspect what are called the massless fluctuations. Around a point in the solution, and basically in mathematical terms, what you end up getting is a complex that looks like this. Yes, sorry, integrating is empty. here when I write EG and EG dual is always the bundle associated to the Lie algebra and the dual. And I'm going to write it here, but essentially A is always the canonical bundle. So you look at what in physics are called the massless fluctuations around a solution. You do this by inspecting what are called the Yukawa couplings, and you recover a complex like this. And
Can you just say again what is this E8?
EG, it's the bundle associated to the Lie algebra.
Ah, okay.
And
I see.
yeah, I said it, but maybe too quickly. And in the cohomological degree of this thing is this, where the one is here. It's not very, I mean, it's important, but what I want to say is that this basically forms the formation obstruction complex, or the virtual tangent bundle to the modular space of solutions to the modular space of twisted quasi-maps. And in particular, this has a nice property, which is the dual of this thing. If you dualize everything, then you shift a bit the gradings around, but you get the same thing back, but shifted by 1. And this basically tells you that you have a -1 shifted symplectic structure. And so this is a very useful gadget, because when you have something like this on such a moduli space, which usually is at the Linear-Mumford stack, but under my assumptions is basically a derived scheme. But under such assumptions, you can define canonically what is called a perverse sheaf, in which you can take cohomology. So our proposal was that the moduli space of, the space of ground states was basically the hypercohomology of this guy valued in this canonical perverse sheaf. And as a check, which goes back to what Justin was saying earlier, if you take MD, so one of the disconnected components, to be the -1 shifted tangent bundle of some variety, MD, then this canonical perverse sheaf is essentially just the constant sheaf that you can resolve with the Durham complex. And so what you get back is that the modular space of states is essentially a sum over Durham cohomologies of MD with some shifts in the grading. So this is a nice check. And then a second proposal that we had is that under our assumptions you can make use of the theory of what is called hyperbolic localization, which essentially tells you that you can localize this cohomology, so this perverse sheaf, to the fixed points under the action. So if we write the fixed points under the action in this way, then essentially what you get by via of this procedure of hyperbolic localization is essentially a space of states that is a sum over the Durham cohomologies of the fixed loci, with some shifts here that I'm not going to talk about in the grading. And moreover,
Do you mean equivariant cohomology?
sorry?
When you say HA, that the proposal is that HA is some cohomology group. Do you mean equivariant cohomology for some group?
No, the Durham cohomology of the fixed
Is
loci.
this standard, and then you're saying localization tells you that the ordinary cohomology is just a sum?
So basically they've got this extra, so there was this extra flavor parameter,
Yeah.
and so he's got an extra action around, and he's, he's not saying that's the same as the original cohomology. He's saying that that's his proposal for the for the cohomology in the presence.
Oh, that's a new proposal, okay.
For in the presence of a mass parameter.
Oh, I see.
The presence of a mass. Yeah, sorry, I'm rushing a little bit, maybe, but and under our assumptions, basically the fixed loci can be described in terms of products of symmetric products of the curve. This is because the associated bundle Ex and Ey split into line bundles, and so the vortex equations are abelianized, and then you can write down the solutions in terms of symmetric product of the curve. And so you can write down the spaces of ground states in terms of
What's the difference between M, ordinary M, and curly M?
Yeah, it's a classical truncation of MD, so you throw away all this odd component.
So which one was the modular space of vortex solutions?
Like the conic modular space is MD, but if you can take into account all the fluctuations around it, is T minus 1 of MD. Right, so now I have only little time left. So let me briefly talk about, so the upshot of this was that you can express under these assumptions the space of supersymmetric ground states in terms of the homology of symmetric products of curves, or products of symmetric products. Now I want to talk a little bit about operator actions. And so we noticed that the Durham cohomology of the symmetric product can be expressed in terms of a Fock space, the graded vector space. And I want to tell you about where this comes from, essentially. So in a in a 3D TQFT, we have operators, local operators, that are defined at a space-time point, and they basically act on the space of states. Justin has started to introduce them this morning, so I'm going to leave the task to him to write them down explicitly. But what I want to mention is that besides local operators, there are descendants of these operators. That basically are defined by cycles. So now I am on this setup, Riemann surface times R, and I'm going to take some cycle C sigma in the homology of this of sigma, and I can define, if it's a one cycle, an operator which is a descendant, which is basically defined on this cycle. So I'm going to take my local operator and define an operator that is supported on a cycle on sigma. And the operation is via this Q mu that I've wrote down there. If you want to know more about it, you can ask me later. And for two cycles, you can do the same, but this time with acting twice with this Q q mu. These operators here are topological, and they're supported on 1 cycles and 2 cycles on the manifold. And in particular, this procedure here is the same that allows you to define the secondary product that Justin talked about this morning.
So what is the interval of the this is the interval of sigma, right?
Yes. Sorry about that. Yes, it's a 2 cycle. And so what I'd like to do is, if you take your QFT in this configuration, and you look at other colored things, yes, and you look at maybe operators that are descended along sigma, then you can define a commutator in the homology of the configuration space of 2 points, which essentially comes from taking 1 cycle where this is before this and swapping them and taking the difference. And this commutator for these 2 operators I claim that you can rewrite it basically in terms of the intersection pairing on the curve and the secondary product of the 2 local operators that you started with. Sorry, 01, 02. And so what you realize, for example, is that this thing here gives rise to nice algebras that act on the space of states. And in particular, if you look at my example of super QD1, we have 2 local operators. They're monopole operators, V plus, V minus. I think Justin is going to talk about them at some point. But what they do is that they create and annihilate vortices at points on sigma. And so if you compute, you can do a QFT computation, compute their secondary product, you get back 1. And so if you select particularly nice cycles on your homology of the curve, you get basically some nice Heisenberg algebras. So here I'm taking G holomorphic 1 forms and then some things that when the intersection pairing with them is 1. So we get some nice Heisenberg algebras like that. Then for a point and the surface, we also get a Heisenberg algebra like that. And basically, the Fock space we had before must represent this Heisenberg algebra. And the way you can construct it geometrically, at least in this simple example, is by trying to mimic what Nakajima, for example, did for the Hilbert scheme of points. So you basically create cycles that create and destroy vortices along cycles. So for example, you define, these are 2 divisor parametrizing solutions to sigma. So I'm almost done. So you define these operators so that their difference lies, it's a point that lies on this cycle here. And similarly, you can define annihilation operators per cycle, where now I am killing a vortex that lies in that position. And these guys will induce operations on my vector space of states that was the infinite powers of the symmetric product of sigma, basically by taking this class in the homology using Kuhn theorem, Poincaré duality, and you can pair the cup product on this, so you get operators that shift you up by 1 and down by 1. And basically these guys here are the ones that realize the Fock space structure of the vector space of states that we looked at earlier. And so the upshot of this is that, so even if you look at very simple structures in the QFT, like these descendant operations, you get nice geometric actions of algebras on vortex moduli spaces and cohomology thereof. And these things should interact with, first of all, with the definitions, the broader definitions that I've tried to give about the vector spaces. And of course with mirror symmetry that I haven't had time to talk about. And so you have mirror algebra actions that are realized on one side on the vortex moduli spaces, and on the other side on things that hopefully Justin is going to talk about at some point. And right. And so yeah, this is.
So the actions are what did you write? What is that? Is the
yeah, sorry.
the homology?
Yeah, this is the Ram's homology of the. Sorry. This is the Durham homology over the symmetric power, right? As I said before, and so you take all these operations, and so these define cycles in the homology of the product, and then you can use Kuhn to disentangle them, and Poincaré duality on one, and then you can pair them one with the other, and you get operations on these homologies.
Sorry, I didn't understand. What is this EN and FN?
So these are supposed to be what are the actions of the monopole operators and their descendants on this particular vector space of state that is given by symmetric products. So they are operations that create and annihilate vortices along cycles on sigma.
Kind of confused, these operations. I mean, this sum, it's sort of known algebraically what it is.
Yeah, that's right. I wrote it down in terms of a Fock space earlier, and when you compute this action, you exactly get the Fock space action. Like one operator brings you up in, yeah. And
How are they related to descendant, the topological descendants there on the left board?
right. So for local operators, it's kind of clear because the local operators, the monopole operators, basically create a vortex at a point. They add, they increase the degree of the bundle by 1, and they do so by adding a point in the divisor. And then you know that you have these Heisenberg algebra relations. And so it was more of a, you have to ask yourself what kind of action does a descendant have? And you can try to write down things that create and destroy vortices, not at a single point, but along cycles. And if then you try to compute the algebraic relations, they are the ones that satisfy. So it's more. You can try to come up with a QFT argument, but I would say it was more like a proposal based on the algebraic relations and what they are, essentially.
We seem to have moved seamlessly from the talk to the questions, which is good, I suppose. Are there any more questions?
So these relations also coincide with what you get if you introduce omega deformation?
Yeah.
But just for local operators, not descendants.
Sorry? Can you repeat?
Like if you introduce omega deformation and look at relations obeyed by local operators, they look the same.
Right.
So, based on also what Justin mentioned, that's not a coincidence?
No, wait.
Well, No, I mean Justin intervene if you like, but I mean, I'm not even sure how we can insert an omega deformation on the Riemann surface in the first place. Can you do that?
Suppose you
An omega deformation on the Riemann surface? If you look at flat space, then, well, yes, the action is similar, right? You have, if you introduce an omega deformation, you have operators that are acting on a point and creating and destroying vortices at that point. And the way in which these things work and the way in which you compose these operations is essentially the same. They're like convolution products.
Maybe I can say one thing. So like this descendant algebra he's building is like taking like the ring of functions on the Coulomb branch, which in this case is going to be just functions on T star C.
Yeah.
And he's basically, he's taking the factorization he's taking the factorization homology of that over his surface.
Yeah,
And
that's
that
right.
just has the property of tensoring this algebra with the cohomology of the surface.
Yeah.
So now you have basically some algebra, which is the cohomology of a surface, tensored with functions on T star C. And then the cohomology has an anti-symmetric form, and the original, has a symmetric form, graded symmetric form. And the T star C has a symplectic form. So if you put those things together, you get an anti-symmetric form on this tensor product. And then he's quantizing that algebra. And like that's not the same as the omega background, because in this case, the stuff that's just coming strictly from the local operators, that's all moving to 0, and that stuff all parameters to 0. The stuff that's interesting is if you take like two opposite Coulomb branch operators and put one in degree 2, like tensoring with the fundamental class, and one like in degree 0.
Yeah.
And that's getting
Yeah, no, that's right. But they would, yeah, exactly.
So basically,
maybe we could discuss this after the session's finished. Should we thank the speaker for the first time?